Before we start the interview, I have two questions about your childhood environment that for me are really important to ask. So where were you born and where did you grow up?
I was born in Washington, D.C. And I grew up, my father was an engineer, and my mother was a food scientist and worked for the U.S. Department of Agriculture, which was just outside of Washington. And they settled in a town which was in those days on the edge of the country, the edge of the city, I would say, in Prince George's County, Maryland. And I grew up there. It was a sort of typical suburbia for the time.
Yeah, beautiful. And later on, you moved to San Diego, where you did your studies, or you did your studies there?
I was an undergraduate at the University of Maryland, which was a couple miles down the street from where I grew up. And I was interested in the brain basis of behavior. And I was in the psychology department, and I worked in a lab there studying the visual system. And I got increasingly interested in that and decided that I would try to go to graduate school to study that. And I did. And I got into Princeton University, which is in New Jersey. It's a couple hundred miles from where I grew up. And so I moved to New Jersey and I studied for a PhD in the psychology department at Princeton. It was an interdepartmental program called a program in psychology and neuroscience. And I got a PhD in 1983, and I stayed on at Princeton to do a different kind of work on the visual system, to learn a new technique. And in 1986, I was offered a job at the Salk Institute, and I moved here to San Diego in 1987, and I've been here ever since.
Wow. You've been there for a long time. And okay, so let's begin with some questions. I'll begin with, you have spoken about neuroscience being relevant to aesthetic judgment. Can you tell us a little bit about your views? Would you like me to repeat the question?
No, it's okay. So the way I apologize.
No, it's okay.
My nose is running.
We need your knowledge. Yeah.
Yeah, my views about this come from an understanding of how the visual system works, and I feel strongly that there are, if we understand the features, the attributes of the organization of the visual system, we can use that to make predictions about how visual stimuli of certain types will impact an individual. And so if the question in architecture is, for example, about how to create a better learning environment, or how to create a better work environment so people are more productive, more efficient, then what do we know about how the visual system is organized? Well, there are two things that are fundamental here. One is knowledge about how cells in the visual cortex. Visual cortex is the cerebral cortex is the part of your brain on the exterior, just inside the skull. It's a big wrinkly part on the outside of your brain. It's the largest part of your brain. It's about 3/4 of the total brain volume. And a large fraction of the cerebral cortex is the visual cortex. And we've learned over the past 50 years or so a lot about how those cells in the visual cortex are organized. And they're organized in such a way that they link together visual features. And by features, I mean, for example, the orientations of contours. Your visual world is filled with oriented contours. The boundaries of objects, for example, are generally contours that have particular orientations relative to one another. And so the visual cortex links together these oriented contours in such a way that you might expect they would facilitate detection of certain kinds of stimuli. And there's a lot packed in that statement. And I don't think I want to go at this point into all the physiological and anatomical details. The point is simply that the cortex, by virtue of its organization, facilitates detection and processing of certain kinds of stimuli. And those stimuli tend to be sort of gradual changes in contour orientation over space. And if you look at the natural world, it's not terribly surprising, given that we evolved in that world, that we should have a cortex organized in this way. Your world is full of contours that are gradually varying in orientation across space. For example, the veins of a leaf or the branches of a tree are things that are extending across space, where the orientation of an edge, for example, is gradually changing across that space. So it's beneficial, because that's the environment in which we evolve. It's beneficial for us to be able to detect those things. And my argument goes a step beyond that. Not only is it beneficial, but there's a visual ease of processing associated with that. And this gets to an idea that was brought forward by the great 20th century art historian, art theorist, Ernst Gombrich. And Gombrich's view was similar. He called this the sense of order. What he was referring to, and he wrote a book, the title of which is The Sense of Order. And what he was referring to is decorative art. And one of the attributes of decorative art, and this is decorative art throughout the centuries of human civilization, one of the attributes of this kind of art is these gradual changes in the contour, the orientation of contours over space. Think, for example, of a cornice frieze. These are often made up of sort of coiling patterns that move across at the junction of the ceiling of a room and the wall of a room. These gradual changes in contour orientation. And you might ask, well, what's the purpose of them? They don't represent anything in particular. Sometimes they represent sort of floral patterns, for example, but they're not intended to communicate anything in particular, unlike many other forms of visual stimuli. They're there because they're pretty. And what does it mean for them to be pretty? In part, it means they provide this visual ease. It doesn't really take any effort to process those kinds of stimuli. They're easily understandable in a way that generally puts them below the level of conscious awareness. And so the argument is that those kinds of stimuli, we fill our environments with those kinds of stimuli. Other examples include patterns on wallpaper. You can look around the built environment and find lots of examples of things like this. Just patterns that have been created by designers and architects that don't serve any real purpose other than the fact that they're patterns. And my argument is that they tap into this native organization of the visual brain and give us a certain ease of processing. Now, the other thing that we know about the organization of the brain and sensory systems in general is that perception is a constructive process. That is to say, we receive information from the sensory environment. In the case of vision, it comes in through the eye. Light is projected onto the back surface of the eye. It's refracted by the lens in the front of the eye, projected onto the back surface, and that's where phototransduction takes place, the conversion of energy in the form of light into neuronal energy. And those neuronal signals are sent up to the rest of the brain, and they're complemented in the rest of the brain, in particular in the visual cortex. They're complemented by signals coming back from memory. Things that you've previously seen, things that you know to be true about the world based on your prior experiences. And so what you actually perceive is a combination of those two sources of information. The retinal information, which is carrying information directly and immediately from the external environment that you're in, and information about your prior experiences with the world. And the reason that's important, the reason that combination is critical, is because the retinal information is fundamentally ambiguous, it's noisy, it's incomplete. There's simply not enough information under most conditions for you to determine precisely what gave rise to that retinal image. There's a little bit packed in this statement, but it's true that there's an infinite number of real worlds that could give rise to any given retinal image. And so if that's true, if we accept that that's true, then how is it that we don't suffer from any ambiguity when we look at the world around us? How do we come to a unique percept, given that there's this possibility of ambiguity about the retinal image? And the answer is context. And context is provided by a number of cues, one of which is the memories you have from your prior experiences with the world. And so these help disambiguate the retinal image, help us construct a percept that makes sense given where we are in space and time. And that's the nature of perception, is that it's constructive in this manner. And so another principle or a prediction one might make about human use of the visual environment is that we could design stimuli that encourage this constructive process. There's something sort of fundamentally satisfying about this constructive process. The great 19th century psychologist William James called it the victorious assimilation of the new. That is, seeing something that is alone, ambiguous, and coming to some decision about what caused that thing to be there. What is the origin in the real world of that stimulus that we've never seen before? And you say, aha, oh, I see. It looks like a chair. They're all manifestations of chairs. Chair design is a huge culture in and of itself. But we can see a chair that we've never seen before and recognize it as a chair, given our memories of what other chairs look like. We're solving that problem, and the argument is that solving that problem is there's an emotional reaction, if you will, to solving that problem. It's very satisfying. We go to art museums all the time and look at things on the wall that are intended to be ambiguous in many cases, and we find patterns in them. There's some artists who criticize that, but it's a natural human tendency to find patterns in things that are not intended to represent anything in particular. And again, it goes back to this evolutionary argument. We find patterns because that's what our brains have evolved to do. And that's critical for survival. We're in a world in which we come across things that we might not, patterns of sensory stimulation that we might not have ever experienced before. And if we don't figure out what it is pretty quickly, it might eat us. And so we've evolved a system for very quick identification based on our prior experiences. And so those are two examples of things that are critical to the way the visual system works, which elicit certain kinds of responses. One of them is this what Albright calls a sense of order or visual ease of processing. And the other is this, what I call perceptual improvisation, which is basically the process of constructing a percept based on the incoming sensory information and your priors.
So this is really interesting and scary, right?
Scary.
It's scary, yeah, because we believe we see things, and perhaps it's just a construction or reconstruction of our memories, bias, and then our visual.
No, you're right. It is a constructive process, but most of the time it works. Most of the time it's pretty accurate at determining what's out there. The goal, of course, I didn't mention this explicitly, I don't think, but the goal is to identify what caused the pattern of light on the back of the eye. And if you take that if you accept that that's the goal, then it turns out that we're pretty good at doing that because these prior experiences are based in reality and based in our prior experiences. And so we don't make mistakes frequently, or the mistakes that we make are of a trivial nature.
Yeah.
It is, however, the case that you can be fooled badly under certain circumstances. If your assumptions are wrong, if your priors are wrong about a particular stimulus, then you can see it incorrectly, and you're absolutely confident that you saw it correctly. A good example of this that we're all familiar with is performance magic. Magicians do things to cause, to basically throw off your priors so that you construct a percept of something that didn't actually happen. And you're very confident about it. The genre of performance magic is such that you know perfectly well you're seeing it incorrectly, but you still have the experience of seeing something that didn't happen or something that doesn't exist. This also happens. I have spent a lot of time looking at forensic techniques that require comparison of visual patterns, and it's now well documented that forensic practitioners make mistakes. They identify the wrong people sometimes. This is particularly true with eyewitness observers, people who witnessed a crime and then come into the police station and identify somebody that they say they saw at the crime scene, and they often make mistakes. And the fact that they make mistakes is documented by a variety of techniques, other forms of evidence, including DNA evidence, which is inconsistent with the identification. And so what's going on in the brains of these people that are identifying somebody? Well, they have prior experiences with the world that cause biases. The situation itself is one in which there's great uncertainty. There's lots of visual noise, if you will, associated with viewing a crime. Typically, the distances are not good. The distances are not good. And I'm sorry, there's somebody at my house right now. Give me 1 second.
It's okay. I'll pause. Wait, I'll pause.
I was talking about that.
Yeah.
Yeah, so an eyewitness will often perceive things incorrectly because there's a variety of sources of noise associated with the witnessing a crime. Light levels are sometimes low, viewing distances are long, the duration of events is very quick, and there are emotional responses and stress layered on top of all that, all of which creates uncertainty. And when we're confronted with uncertainty, we do this natural thing. We fill in the blanks with what we know to be true, without being aware of the fact that we're doing that. And sometimes the things that we know to be true are not appropriate to the context. So we fill in, we, for example, know from reading news reports that criminals sometimes carried guns. And so we might say, well, there was a gun at the crime scene, even though there may not have been a gun at the crime scene. We're expecting it to be there, and our percept, which is constructed, as I said before, our percept integrates that information.
Wow, this is so interesting. You know, for the legal system, this should be so helpful, right? To introduce.
There's been a lot of interest in this recently, particularly eyewitness identification, because there's now lots of evidence. Most of this comes from analysis of DNA from people who have been in jail for a long period of time. And there's something, typical cases, something sort of suspicious about the conviction for this guy who's been in jail for 15 years. And a group of lawyers there's a legal advocacy organization in New York, based in New York, called the Innocence Project, and they've advanced this quite a ways. And they will go to a judge and ask for permission to reanalyze the DNA, or maybe the DNA was never analyzed properly to begin with. There are now much better molecular biological techniques for doing that. And they find out that the DNA from the crime scene is not the DNA of the person who is in prison. And then you can ask, well, what's the reason why they were convicted to begin with? And
bias.
Well, ultimately bias and uncertainty, but typically the conviction in those cases, the conviction is like 70% of the cases. The conviction is based on eyewitness misidentification. So the eyewitness said that's the guy, but the eyewitness was wrong. The guy went to prison, spent 15 years there, and finally we find out that his DNA is not compatible with the DNA of the crime scene. So we know this happens, and there are lots of laboratory studies in which you can demonstrate that people make mistakes in eyewitness identification. I mean, these are, in a laboratory, these are typically done with staged crimes. So it's not a real crime, and the subjects are aware that it's not a real crime. So it doesn't have the same emotional or societal impact.
Yeah.
But there are conditions that mimic those of the real world, and people are pretty terrible at identifying correctly under those circumstances. And there are lots of biasing factors that can throw people off, which can be the cause of this.
Yeah, that's absolutely, this is sad. It's absolutely sad, you know.
Yeah,
But,
but the scientific community is
rolling up their sleeves to help, and I'm so proud, you know, that you are doing this and to offer something to the world that no one has ever changed. This has not evolved the way we judge, you know.
Yeah, you know, things are changing as a result of this science, and I'm very happy about that. I'm happy to be part of it.
You should be so proud. Now, second question. Does visual work in memory play a role in navigation or visual planning?
Visual planning, yes. I mean, one of the things that we've studied in my laboratory is visual imagery, as you would imagine. A lot of what I was just talking about is visual memory.
Okay.
That is sort of filling in the blanks. It's a type of imagery that is different from what most people think about. There is explicit visual imagery where, you know, I don't know where my keys are, and so I try to imagine the kitchen counter when I left the house this morning, where my keys sitting on the counter. That's explicit visual imagery. That's imagery that I'm conjuring up for a specific purpose, an image in my head. The other form of imagery is implicit imagery. And that's imagery of the sort that I was talking about earlier, where my brain fills in the blanks with information based on my prior experiences. And I'm not aware of the fact that that's going on. And we've studied this a great deal, and I think it plays a fundamental role in the experience of architecture. You're in a novel space, and you're trying to find your way. I mean, navigation is a very specific problem that people face in certain built environments. And I'm trying to find my way, and so I create images in my head, and different people do this to different degrees. Some people are very good with sort of spatial imagery, and other people are not so good. But I create a model in my head of what the space looks like, which then facilitates my ability, either correctly or incorrectly, facilitates my ability to navigate through the space. And we do this all the time, and it's a sort of I was involved in a conversation recently about the role of imagery in general in the experience of architecture, and I really think it is fundamental.
Okay, so talking about architecture, what should architects take as the key ideas from your views or on familiarity and novelty?
Well, familiarity and novelty, those are words that were used, although not verbatim. It's a common distinction in psychology, familiarity and novelty. Then we have lots of reactions to things that are familiar and different kinds of reactions to things that are new. And that's been known for a long time. What Gombrich was referring to is the distinction, the same distinction I was drawing earlier, between things that are restive, things that are visual patterns that give us the sense of visual ease, that we immediately understand them, it doesn't require any extra processing. And at the same time, we also need the experience of visual problem solving, perceptual improvisation, that is encountering things that we don't understand and gaining the satisfaction of figuring them out. And so those are roughly what I was referring to as familiarity being the visual ease, and novelty being coming across something that you've never seen before and trying to figure out what it is.
All right.
And so my views on this are, again, rooted in knowledge of how the visual brain works, as I was speaking earlier.
Perfect. Okay. I believe you worked with an architect on the design of a learning environment. What ideas did you bring to the table, and did they work?
Yes, this was a project that was initiated by an architect, a rather visionary guy named Jim Detterman. Jim Detterman works in an architectural firm in Baltimore. I've forgotten the name of the firm, although it's important to know. I just can't remember.
We'll mention it under the video. I will find it.
Yeah. And Jim heard a talk that I gave at a National American Institute of Architects meeting, I think about 10 years, no, maybe not 10 years ago, maybe 8 or 9 years ago. And it was about the things that I've been talking about how certain visual patterns tap into certain parts of the visual brain. And he got excited about this because he had an opportunity, or he knew of an opportunity, to do an experiment in a charter school in Baltimore. And he was inspired by some ideas from a sort of biophilic design.
Yeah.
And biophilia, or biophilic design principles, are not explicitly rooted in how the brain is organized, like the ideas I've been talking about, but the end result is the same. That is, we ought to have this affinity for visual patterns in which there are gradual changes in the orientations of contours. And the reason, of course, is that we evolved in those kinds of environments. So the biophilia community was arguing that we ought to put patterns in classrooms that mimic the natural world. And I was making essentially the same argument, but for different reasons, because those kinds of patterns tap into this native organization of the visual cortex. And so Jim brought this team together that I was part of, and he heroically, I would say, managed to get human subjects approval to do this. It's a charter school. It's a public school in Baltimore. And he had to get the school district to give him permission to modify a classroom. And we did two things in this experiment. We modified visual patterns in the classroom, and those visual patterns were based on the principles that I was describing earlier. That is, a lot of these sort of gradually curving lines on the walls, on the carpet. And again, those principles are in line with the biophilic design principles as well.
It's like biomimetics, biomimicry.
It's mimicking attributes of the visual world, the fauna and the flora in the visual world have these attributes, and so that's what we created in this environment. We did this in one classroom. So there's a control classroom, which is unmodified by us, and there's an experimental classroom in which we put these patterns, and that's the independent variable, the manipulation of the classroom. The dependent variable in this case is two things: one, academic performance,
Okay.
and two, stress. And so we measured academic performance using standardized tests. These are tests that are given to every kid in the school. This is a state mandate, and every kid gets the same kind of test at the same time of year. And this is true both in the experimental classroom and in the control classroom. And so we can measure academic performance in a relative sense from those tests. We also measured stress levels using heart rate variability. It's not the best measure of stress, but there is evidence that variability in heart rate, and what we're looking at here is the interbeat interval. So if your heart is beating at a constant rate, then that interval will be constant. It may be, 40 milliseconds, but it's a constant time. And it turns out, the evidence suggests that if your heart rate variability is relatively high, that is, there's a little bit of jitter in the beat length between different heartbeats, that's an indication that you are less stressed. If your heart rate variability is low, that is, the interval between beats is always exactly the same or very close to it, then that's correlated with higher stress.
Okay.
So we measured stress using, there are better ways to assess stress, but again, these are school children. There's a middle school, and there are limits to what we can do. We wanted to use
Dermic?
there are a variety of things you could use. You could use galvanic skin response. You could use a product of your body, so called cortisol, which is associated with stress. And you can find cortisol concentrated in the saliva. And in principle, you could measure salivary cortisol levels, but the school district wouldn't allow us to do that for concern for the children. And that's, I understand that those are constraints when you're operating with children in the real world. You don't want to do anything that might be harmful to them or perceived as harmful. So anyway, we used this interbeat interval, which was easy to obtain. The students put on a little sensor several times a day, and the sensor measures your interbeat interval. If you wear, a smart watch, for example, the watch I have on my wrist gives me my heart rate, and also gives me my heart rate variability. So these things are easy to measure relative to salivary cortisol levels. We did that, and we measured academic performance. And it turns out that in the experimental classroom, the one in which we'd modified the design of the classroom in ways that I described a moment ago, academic performance was better, as evidenced by higher scores on these standardized tests and consistently higher scores across time. And stress levels were reduced, as evidenced by an increase in heart rate variability in the experimental classroom relative to the control classroom.
And what happened to the other non-control rooms?
They were, well, they were lower than the experimental classroom. And we don't have any way of knowing whether they were any different from any other middle school classroom in any other school. All we know is that they were lower than the experimental classroom in this study. And it's a single study. It's one class. There are lots of interesting things in the results that deserve follow-up. but I'm pretty excited about it. We did this, we presented this at the National AIA meeting in 2019, just before the pandemic, and haven't done anything since. I think Jim Detterman, because he's employed as an architect, has been designing the built environment, but I know he remains interested in this topic, and maybe at some point we'll do something further with it. But it's a nice first step in trying to use scientific principles to design a classroom to improve performance.
That's so beautiful to know. I mean, to know that our kids will have at least the chance to have better learning environments, and not the same environments where probably our grandparents used to have the same.
Yeah,
Changed.
I mean, this is why I'm excited about this study and very enthusiastic, is that there are lots of potential applications of neuroscience knowledge in building design. But it's hard to think of an application that's as significant as this. There's hardly anything more important in our world today than the education of our children.
Yeah.
And so finding ways to do that better,
that's not
against that. Yeah.
Yeah, that was beautiful. Okay, to continue. How might the study of vision deliver constraints or recommendations for the design of very large environments?
Well, I'm not sure what you mean by very large. I mean, an airport is a good example.
An airport. Yeah, let's talk about an airport.
Airports
you go
are
inside,
generally,
and then you already when you enter, you feel cold. You have a lot of people.
And you're stressed because you have to get someplace, and timing is critical, and you're in an unfamiliar environment with a bunch of strangers, and all of which naturally leads to kind of adverse reactions on the part of individuals. And so one question is, how do you get information conveyed to a traveler quickly through the visual sense? And we do this typically using these there's a name for these boards, I forget what they're called, these big things that hang from the ceiling that show the name of the city and the the gate information, the time. Yeah. And they're generally hard to see, and there's so much information on them that's not relevant. It's difficult to find the information that's important to you. And so, and that's sort of an obvious behavioral or cognitive observation. And there are ways to modify that sensory environment such that you can more easily grasp that sensory information. And I think that a studies of sensory processing and visual attention in particular in this case can be beneficial to the design of those kinds of environments. There's also, as I was talking earlier, this issue of imagery. So if I have to be at a certain gate and somebody shows me a floor plan with the gate on it, a lot of people are completely incapacitated by that. A floor plan doesn't mean anything to them. They can't interpret where they are relative to the other place on the floor plan. And so what we need are ways to facilitate your ability to imagine that in 3 dimensions.
Okay.
And there may be ways to design visual stimuli that they give you that greater sense of imagery as you're moving through the space. So you can sort of imagine, well, if I go down this way, I've been in airports, I have very good visual imagery, and I have very good spatial orientation abilities. But I've been in airports where I just think, I'm completely baffled. I have no idea how I got here and how that relates to the place I came from. And that's frustrating. I mean, ultimately, I find my flight because there's enough signs everywhere. But it is frustrating. These are big spaces. They're often, we very rarely build new airports from scratch. We being people, we don't usually build new airports from scratch. Occasionally, a new city decides it wants a brand new airport, and that happens. But mostly airports, you think of the airport in Frankfurt or Heathrow, and those are airports that have been added to bits and pieces over decades, and so it's just a rabbit warren, and people don't have a good sort of map in their head of where they are relative to anything else. And so I don't have a solution to that problem, but I am convinced that a better understanding of visual attention and visual imagery will help facilitate a solution to that problem. Mm-hmm. So that people have a better sense of where they are, which would help, I think, both reduce anxiety and get them more accurately to their gate in a timely fashion.
That reminds me of the term affordances, right?
Yes, that's right. Hold on one second. Sorry, I had to pick up something. Yes.
It's like affordances.
The environment has to afford the opportunity for you to imagine where you are in space and time. And that's, again, this is particularly a problem in these older airports that have been that have grown over time with little bits and pieces sort of tacked on to an existing airport. I'm trying to think of an airport, a modern new airport.
Dubai. Dubai, Singapore. Singapore is a little bit biophilic, but Dubai, Madrid, I'm very bad with visual orientation, and I need affordances. Yeah,
and I'm trying to conjure up in my head what Madrid airport looks like, and I can't.
It's huge. You will get lost even with affordances. That's a problem.
But there are, one strategy is to make the airport a large open space, so that rather than having, and again, I use Frankfurt as an example because I can remember walking down these hallways where you don't know what direction you turn, and then you lose your orientation, and suddenly you're out in some atrium and you wonder, how the heck did I get here from where I was? And this, I think, this lack of understanding of where you are in space and time in that kind of environment, I don't know if anybody's ever done a study of this, but I imagine it increases stress levels. It probably generates a certain amount of confusion on the part of a traveler and anxiety. So having a large open space affords the ability to sort of see where you're going from where you're standing, as opposed to walking down a series of hallways.
So a recommendation would be affordances to ease.
That's one way to put it, yes. There are, I think, a careful examination of the sensory and cognitive attributes of an environment could give you ideas about how to design it better. And I imagine that most modern airport design firms, those architectural firms that are involved in designing airports, are thinking about this now. But again, it's a hard thing to do if you're just adding a piece onto an airport that was originally built, say 60 or 70 years ago.
Yeah. Okay. Do you think the idea of atmosphere can be refined enough for scientists to work with architects in a helpful manner? Atmosphere, you don't have to answer this. That was just me with this concept of atmosphere, but
it's an interesting idea. I just need a better definition of atmosphere. Atmosphere is a colloquial term, and it means lots of different things.
Exactly. There is no one definition.
Atmosphere is up there. That's not the atmosphere you're talking about. You're talking about something that it's a term that I think is, I'm not an architect, but I think it's a term that's commonly bandied about in architecture. And as a scientist, I'm open to the idea of helping, but I need to know what the definition of the word is. and without a concrete definition,
yeah, it's difficult. And you're not the only one who tells me, no, forget, we are not going to talk about atmosphere. And it was just, okay.
Well, I can say this relative to that question, that the experience of being in an architectural space is highly multidimensional. There's so many variables that go into that experience. Attributes of the environment that you're in, the emotional state that it elicits in you. And so all that together is somehow creating an atmosphere that you experience. But that's sort of obvious. And I'm not sure that we need a particular word to define it. And the word has so many other connotations that I don't think it's useful unless somebody tries to define it.
Yeah.
Is atmosphere the height of the ceiling? A higher ceiling, people are generally more well-adjusted and less stressed if the ceiling is high. That's something that is testable, and it's been tested. And so if we can create an experience like that, create that kind of atmosphere, then that's a good thing. But you have to then define atmosphere as, in that case, I defined it as
There is
the
no
ceiling.
one. There is no one definition on atmosphere. I've been researched. I mean, there is many, and there's no one. And then I get confused, and I understand you. It's interesting to know that you can be in one place and experience two atmospheres, being here, sitting here. But how science can help us, I don't know. But I wanted to.
I think it can help us if we define the term. I mean, that's the challenge, and it's a challenge I offer to the architectural community, the design community. I'm prepared to address it, but I need to know what is meant in that community by atmosphere.
So this is a challenge that architecture is also facing, because I know they're been debating on this term for a long time too. So yeah. I think it's going to take a while before we can define. But yeah, are you facing challenges currently with anything related to any topic that is giving you like headache?
No, I think about these kinds of things all the time, and I enjoy it. I have the luxury of being a scientist, where I can think. I like the fact, I started studying the visual system. I got into neuroscience. I got my PhD almost 40 years ago, and I started, even as an undergraduate, I started with an interest in neuroscience. And like most people, I got into the field, although I was particularly interested in visual perception, I got into the field with the idea that the application of neuroscience knowledge is medicine. That is, we learn more about the brain, and like most sciences, there's an applied aspect, and the application of neuroscience knowledge is better clinical treatment. We can treat people whose brains are broken or diseased by knowing how the brain works. And I still believe that's true. It's just in the visual system, it's pretty complicated. We've learned an enormous amount so far, but we're not, with a few exceptions, some having to do with the retina. The retina is only a small part of the visual brain, but because it's small, it's pretty well understood, and there are pathologies of the retina that can be addressed clinically. There are even now retinal prostheses that somebody who has photoreceptors that are not working, you can get a prosthetic device. They're crude at the moment, but they will get better. So that's a medical application of neuroscience knowledge. But they're few and far between. And I realized at one point that, if you're studying the kidneys, the only reason you'd study the kidneys is to improve medical practice. Yeah. Because, I mean, the kidneys might be interesting in and of themselves, but the application in the real world is medicine. but the brain is different. Yes, there are pathologies of the brain, and we want to gain knowledge to help treat them, but the brain controls behavior and perception and cognitive experience and pretty much everything that people do. And thus, an understanding of how the brain works is relevant to all sorts of problems that individuals have and that societies have. And once I realized that, and I know a lot about the visual system, I started trying to apply that knowledge to other problems in the real world. A forensic practice, for example, much of forensic practice involves visual pattern comparisons, and I know a lot about how people compare visual patterns and the errors that can happen given the way the visual system operates. So that's a satisfying thing. It's treating a societal problem with scientific knowledge, and architecture is the same way. There are the problems of design that limit the capacity of people to do what they want, become educated, for example. Healing, so somebody who has a disease or some kind of pathology to the body, the question there is what kind of environment is best for facilitating recovery from that. And so an understanding of how sensory systems, particularly the visual system, work and how they feed into to visual motor control, your ability to move about your environment, the emotional responses you get from that environment, that's all beneficial to design. So these are the things I think about all the time, and every now and then we do an actual experiment and add to the evidence, the body of evidence that is growing now because a lot of people are interested in this topic.
And what are you working on now that is relevant for architecture, for example?
I'm doing, this is a study that I'm doing with, collaborating with my colleague Sergei Gepstein and collaborating with the Los Angeles County Museum of Art. This is one of the world's great art museums. It's the largest art museum in the western portion of the United States, and it has a fabulous collection. And so we connected with the people who run the LA County Museum of Art and thought for a long time about what sort of research project we might want to do. And we spent actually more time on that than thinking about it than we had originally planned because the pandemic made it eventually
difficult.
This team of people, we would have regular meetings to discuss a plan, and then we just started having Zoom meetings periodically to discuss a plan, and that went on for a while. And then finally, I realized that there's a new technology available. It's called computational ethology, and the Salk Institute, where I work, had just recruited a new investigator. His name is Telmo Pereira, who is one of the pioneers of this new technology. And basically, it's a technology, it's been, for the most part, applied to studying the behavior of animals, experimental animals like rats in a laboratory or insects. And it involves tracking every aspect of the animal's behavior using video techniques and machine categorization of behaviors. So, for example, if you have a couple of rats in a cage and they're just wandering around, you have these video cameras and you track them on video everywhere they go. And then you have a sort of computational process operating in the background that extracts characteristic features of behavior, like the amount of time the rat spends sort of grooming his snout. Rats will like rub their paws on their snout, for example, or the amount of time the rat spends on the running wheel, or the amount of time the rat spends with another rat in the same cage. all these things can be characterized in fine detail, and Talmo knew how to do that. It's a bunch of high-powered computers and computational techniques that I'm not an expert with. And so Talmo joined our team, except this time, rather than studying animals in a cage, we're studying people in an art museum. And so we, again, in collaboration with the LA County
They're
Museum,
animals, no?
they're animals, yes, they are, yeah. They're a little bit more complicated in many ways. The things that drive human behavior are, to a large degree, socially and culturally determined in ways that we wouldn't normally say is true about other animals. Anyway, we have the LA County Museum gave us a gallery to work in for this experiment. And we got a grant from the National Science Foundation to do this. And the experiment involves putting a series of cameras around the room. The room is about 25 feet by 50 feet. And the ceiling is 20 feet high. And it's a collection of ceramic objects that are being displayed. The objects are all from the museum's permanent collection. And there are themes associated with both the history of these objects, the materials that were used. And so they're related in some complex way, which is dictated by the exhibition designer. So this is a group of people who work for the LA County Museum, and they arrange things in the room. And these objects are on platforms. So unlike paintings, which are typically on the wall around the perimeter of the room, these platforms sit at different locations in the room, and the exhibition designers position them so that when you traverse the gallery, you move from one to another in a sort of predicted way, and with the hope that the layout of the room will maximize information gain, that is, maximize learning and optimize the experience for a visitor. But we can actually empirically determine what people do now when they enter the gallery.
Wow.
Because we have all these cameras. And I should stress, everybody's anonymous. We have no idea who anybody is when they come into the gallery. We don't have any tools for trying to recognize people. And so we can collect data on many thousands of people as they come through the gallery. And so it's a huge database. And we're now in the process of developing the algorithms. These are modifications of algorithms that have been developed for use in animals, for the use with people. I mean, there are a number of different features. People are two-legged rather than four-legged. People wear clothes, and those clothes, say somebody's wearing a red jacket, that facilitates your ability to track that person uniquely as they move through the gallery and distinguish them from other people, which is a big part of the computational problem. And you have all these people sort of moving around in the gallery, and you want to make sure that you keep the same individual identity. And again, their real identity, we don't know, but their identity in the gallery is maintained as they move through the space, that we don't confuse one person with another person.
That's difficult, no?
It's difficult, but we have
that's a challenge.
It's a challenge, and and we have the best people working on this problem. We have a terrific postdoctoral fellow by the name of Eric Leonardis, who's working on this, and he's developing a lot of the techniques for analyzing the data right now.
Wow, that sounds complex.
Yeah,
a lot of work. Huh?
It's a very exciting project, in part because I've been studying the visual system for a long time, and its influence on behavior. We do it in the confines of a laboratory where everything is controlled. And this is a laboratory of sorts, but it's a laboratory that presents a sort of semi-naturalistic environment, an environment that has many properties of the real world, but is not as, I mean, the real world is really complicated. An art gallery is a little complicated, and more so than a laboratory experiment.
Yeah.
We're able to make decisions autonomously. We don't control what they're doing. We just monitor what they're doing. And we can make predictions about how the environment influences their behavior, which is the ultimate goal, is to understand how this environment determines what somebody will do. And can we alter their behavior in a beneficial way so that we maximize their experience, and maximize here is euphemism for improve learning, improve the emotional outcomes.
This sounds like, yeah, in a beneficial way, because we are experiencing the environments now in a really negative way. I mean, not everyone, but the way we are living in our designed buildings right now are not made for us. So I think this is a great job that you are doing. And another thing that I realized about the human behind the scientist that you are is that you are a happy person doing these things. It makes you more happy.
Yeah, it's I like doing science. And I like doing science that has relevance to the real world. It's the most satisfying kind of science that I've ever done. I've been doing science for a long time. This work on forensic practice, for example, is incredibly satisfying to me, because I can, based on the things that I know to be true about how the visual system works, I can make the world a better place.
That's so beautiful. I told you this before, and I will repeat that this is the best thing that I can get from this interview, you know, because all this information will be difficult for me and even for the audience to process. Is a lot. But one of the aims of these interviews that I do is to get to know the human behind, sometimes the architect, sometimes the scientist. And I realized something about you in this interview, and is that you are happy, and you're happy talking about all these things that you do, and they're all different. And it's mainly because you want to help to make a better world. And I think this is novel and fantastic.
Yeah,
Thank you for that.
Well, thank you.
Thank you.
Thank you. Yes, I'm happy, and I have the privilege of doing things in life that are interesting to me and beneficial to the world.
Well, and thank you so much for this interview.